In this video, we're going to be talking about the central limit theorem, which is a very important theorem in statistics. But we're not going to start by talking about the mathematics behind this theorem. Rather, I'm going to show you some experiments which will helpfully give you some of the intuition behind this important result. So right here on the screen, I have a grid of pegs. And what I'm going to do is I'm going to drop a ball from the top of the screen, and when it hits a peg, like this peg at the top, it can either go to the right or it can go to the left. There's a 50% chance of it going right, a 50% chance of it going left, and every time it hits a peg, that decision is made again. So once I've hit this peg, if I move to the left, then I can go to the right, or I can go to the left, again with a 50% chance of moving in either direction. So just to show you that briefly with a couple of balls, you can see they work their way down the grid. They might go left, they might go right. Now I'm going to start running this experiment a bunch with a lot of balls. I want you to sort of keep track of where these balls are landing. So one just went into this 10. That meant that it had to go to the right 10 times in a row. What are the chances it goes all the way down into the 0? That means it has to go to the left 10 times in a row. Where are most of the balls landing? You can sort of see sort of in the center here. And if we increase this speed a tiny bit, just so we get more results out, I'll then stop this process. We'll let the last few filter down. This histogram at the bottom is keeping track of where all the balls have landed. So most of the balls have landed in this central bin, meaning that as they've worked their way to the right and to the left, to the right, to the left, many paths have led the balls into this bin labeled 5, meaning it's gone to the right 5 times. So these numbers at the bottom you could think of as keeping track of the number of times I've gone to the right. So never went to the right, I always went to the left, or a 10 would be I went to the right all 10 times. So this histogram approximately follows a normal distribution, which was the topic of the last video we discussed. Okay, now I'm going to do a completely different experiment. Let's see. So here, what I'm going to do is I'm going to roll some dice. So I'm going to roll specifically 5 dice. And I'm going to count the number of faces on those dice. So let's just pull up a picture to help explain. So let's see. I'm only going to roll 5 dice here, okay? And then I'm going to count the number of dots on these faces. So if this was my roll, I would have 10 from the first 2, plus 5, 15, plus 4, 19, plus 1, 20. So I would get a result of 20. The smallest possible result I could get is if all these dice wound up with a 1, right? Then I would get 5. And the largest result is if they all came up 6s, in which case I would get 30. So this applet here is going to roll those 5 dice. In the background, it will just tell me the number of dots I see at the top. So I roll once, and I got a 15. Okay, I'm going to roll again. Now I got a 23. I'm going to increase the number of rolls I do at a time, just like we ran a lot of balls at once. And I'll start to see a distribution of what the most likely rolls are. Okay, and then you'll see that this starts to take basically the same shape. If I run it enough, it will sort of stop moving around, and it will take this normal distribution shape, just in the exact same way as a completely different experiment where I was just dropping balls on pegs and seeing if they went right or left. And this is the power of the central limit theorem. It says that if I have many independent experiments, then the sum of those experiments under normal conditions will follow a normal distribution regardless of what distribution those experiments are coming from originally. So to sort of highlight this point, I'm going to pull up a third applet here, okay? And what I'm going to do is I'm going to run an experiment that follows this very curved distribution, okay? So this looks nothing like a normal distribution, and I'm going to take 5 samples from this distribution. Okay, so I got 1 over here, and I got 4 more over here where most of the weight of this distribution was. That makes sense. And then I take the average of those 5 different experiments and I plot it down here. Okay, I'm going to repeat that process very much in the same way that I repeated the process with the dice or repeated the process with the pegs. I'm going to do this a bunch. And so you can sort of see it's always very likely that I'm going to get observations over here. Less likely I get them out here because this tail is so light. But you'll start to see these observations cluster over there. I'll run this maybe 2 or 3 more times, and then to save ourselves some time, I'm going to run it 10,000 times at once. And what's going to happen? It's going to look pretty normal. Let's do another 10,000, and another, and another, and another. And you'll see that I get out this same normal shaped distribution as what I saw in the previous 2 experiments. Okay? And this is going to be true no matter what distribution I make up. So I'm going to make up something that looks not at all normal. So there's a certain probability of getting these lower numbers, and then maybe there's a bump in this middle, and then you cannot get any of these numbers in between. And then there's again a high probability of getting something out at the end. Okay, so I'm going to take observations from these 5 at a time. I'm going to plot them down here, just as I did before. And if I do this a lot, if I hit this 100,000 button, I'm going to start getting something very normally distributed. So if I do this enough, that will smooth out and give us that normal curve that we're used to seeing. So what the central limit theorem says, the bottom line of the central limit theorem, is that if I have independent observations coming from any type of distribution, it could be as crazy as the one I just drew at the top here, if I take their sum, also if I take their average, I will get out the normal distribution if I repeat that process over and over again.